Hello, everyone. Welcome to the Southern Plains Climate Science webinar series. I'm your host, Cody Nguyen. I am also the operational assistant for the South Central Climate Adaptation Science Center, also known as the South Central CASC. Today, I am pleased to introduce Dr. Matthew Levi, who is an assistant professor of soil science in the Department of Crop and Soil Sciences at the University of Georgia. His research focuses on the nexus of soil, vegetation, and water at the landscape scale, with an interest in improving natural resource planning and sustainable land management. Dr. Levi is also a co-investigator on the South Central CASC-funded project titled Wildfire Probability Mapping Based on Regional Soil Moisture Models. And today he will speak about some of the recent advances in predicting soil moisture in the Red River and Rio Grande basins, which were identified through this project. He will also speak on how this information could lead to an improved understanding of wildfire across the region and how that benefits fire managers. Welcome, Dr. Levi.
Good afternoon. So I am a co-PI on this project, and I first want to recognize that we have a pretty big team that has come together to work on this big question. The PI for the project is Dr. Tyson Ochsner, and we've had a variety of folks that are representing soil science, remote sensing, meteorology, forestry, and geography, including the original team that started off with this proposal and subsequent work, including Grant Snitker, Eric Kruger, Kevin Acheng, and Miguel Villarreal. But over the course of the last couple of years, we've actually accumulated a few more collaborators, and these collaborators represent a range of expertise and spatial location across North America. So what I'm going to show today is some of the work that has resulted from this diverse team, and try to show what we've learned so far with respect to understanding soil moisture at a regional scale, and then also how it relates to fire. So as you're all members here in the audience, you're probably interested in wildfire. Many of you probably have a great deal of experience with fire, maybe you're on the ground, or maybe from a modeling perspective, or maybe you've experienced it firsthand in other ways. So globally, wildfire affects nearly 150 million square kilometers each year. So that's a huge footprint. Many of these areas are burning repeatedly in subsequent years. In the US, we average about 38,000 square kilometers annually between 1998 and 2017. So you can see on the image here on the right, you can see a map of the areas that have burned with large fires within the US between 1984 and 2015, essentially taking out the effect of multiple fires layering upon one another. So you can see areas that have simply burned based on this monitoring trends of burn severity database. And if we look also at some of the numbers from this database, you can see that since 1984, we've had this steady increase in the areas burned across the US. And so this, obviously promotes a lot of interest and need for understanding how to understand this situation better, in particular because the federal fire suppression cost in the US in 2021 actually topped $4 billion US. So it's a significant problem, and it seems to be of growing concern. So oftentimes, when we think about fire and trying to understand how that soil might come into play, we often think about, well, all right, we had a fire on the landscape. So what happened to that landscape? What's it look like? What happened to the soil? What's the burn severity? What are the potentials for erosion from the area, right? So this is a typical question that we often think of. But if we're trying to understand the fire, and maybe try to get a better opportunity to predict when those fires and where those fires might occur, then we might start looking at some of the properties that drive fire likelihood. So traditional covariates that have been used include a number of climate variables related to temperature, precipitation, obviously, vapor pressure deficit, and others like wind speed. But we also have to consider what the fuel condition is like. So what's the fuel load? What's the fuel moisture content? What's the connectivity of that fuel? And is it fine fuel or is it more coarse types of fuel? And of course, we need to have some kind of ignition. So in wildfires, of course, we're thinking of things like lightning. That's the obvious situation. But also, we have to think about fires that are occurring in more urban areas near that wildland-urban interface. So ignition variables are really common for understanding fire. And then, of course, topography comes into play when we think about fire spread, right? So we're trying to think about these things that control where the fire might start, and then how large it might get, which direction it might grow. So being a soil scientist myself, I often think about, well, how can soil plug into this equation? And the natural fit here is that soil is the sponge that essentially absorbs moisture from the climate, from precipitation. And of course, it's losing moisture through evapotranspiration. But then it's also providing the situation and the necessary components for this fuel load to develop in the first place. And not just the amount of fuel in a given year, but also the type of vegetation community that we might experience in a given biome. So the key to that situation is primarily the soil moisture that's related to things like fuel moisture and sort of integrating and holding on to this climate memory or weather patterns. If we look at the global landscape, you can see mean soil moisture, the annual soil moisture between 1979 and 2013. So this is about a 35-year span from the ESA Global Soil Moisture Database. You can see the trends in soil moisture and volumetric water content, where red would be dry areas and the blue shades would be the wetter zones. And this is no surprise to us. But if you start thinking about how does this relate to the areas that are burning, this is results from the Global Fire Emission Database, summarized in this 2019 paper here for a similar period, 1997 to 2014. And so I just want to sort of call your attention to some of these hot spots, if you will, lots of areas that are having repeated burned percentages each year. And so these are the areas that are on the semi-arid margins for the most part, right? So there's this relationship between soil moisture and vegetation communities, and as well as how that relates to the fire. So kind of building on some of the basics here. And now if we think about our knowledge of soil moisture as a predictor for fire. So now that we recognize there's this important situation where obviously soil moisture is related to things like fuel moisture and the curing rates of different fuels and vegetation. There's been evidence from several recent papers over the last decade and several prior to this that indicate that fuel moisture is definitely related to soil moisture. So that's one of our important variables for a fire. Also, recent work has identified that measured soil moisture values can directly be related to things like wildfire size. In this particular study by Kruger et al. Looked at grasslands of the Southern High Plains. And so continuing that work, they also found that this traditional Keach Byram Drought Index, which is used across the contiguous US as a standard, is actually not as good as measured soil moisture. So you might have noticed that I started this little equation here, this line showing that the evidence is growing over time as we learn more and have more studies, that there's more evidence for using soil moisture as a fire danger predictor. If we continue some of those lines of evidence, you can see that we have the potential to model soil moisture for large areas, such as this study that looked at the soil moisture conditions across the western part of North America and forested landscapes, and found that modeled soil moisture is also related to wildfire occurrence across that region. And then we have obviously remote sensing platforms now that are focused on soil moisture predictions at global scale and for smaller areas as well. But several recent papers across the globe actually have been proving that soil moisture conditions can be predicted with remote sensing, and then that info can be applied to understanding wildfires for different regions. So one could hope that this might be a linear relationship. It's probably not linear, but I do think we're definitely in this the cusp of a new era in understanding soil moisture contributions to fire danger systems. So soil moisture is great, right? We know that we have the potential to apply this information to wildfires, to drought, etc. So what do we have for soil moisture information? Well, we have point data from a variety of climate networks, as you can see shown here from the National Soil Moisture database. So you've got different networks managed at the state level or other regional levels and some at the national level. But even though we have so many networks that are linked together now, we have limited distribution. As you can see, there's a lot of space between these measured values, right? So how do we scale that information? How do we best tie that into the potential danger for fire or otherwise? So one way to scale is to use satellite-based platforms, as I mentioned. We have several of these now. One drawback is that they focus on the surface properties. We do also have mechanisms for linking models to extend those surface predictions deeper into the root zone, but those are based on some, other properties of the soil. So we're making progress, but there's still some limitations for using satellite data. Also recognize that we don't have satellite data going back for as long as we've been measuring soil moisture. So this is also a drawback when we're trying to understand what's driving wildfire on the landscape. One of those examples of integrating soil moisture data from models as well as those with remote sensing is this SMERGE data set. So this is essentially one attempt at modeling long-term soil moisture for several decades. The drawback to that data set is that it's a large spatial footprint. So we have large pixels this is 0.125 degrees for each pixel. And then we have land surface models that we can sort of insert information such as soil properties, vegetation communities. We've got climate information. And so we can essentially turn the dials on these components to try to understand the soil moisture at a given time or place. So our objectives were to develop an effective model of soil moisture for the Red River and Rio Grande basins that would provide sufficient detail in the temporal resolution, the spatial resolution. So what's the pixel size, and then also with depth, because we're not quite sure, which depths are most important if we're trying to understand soil moisture. If we measure the surface soil moisture, it's going to be a lot more dynamic than measurements deeper within the profile. And so some combination of linking remote sensing data to have spatial connectivity to measured values at point locations, and then of course incorporating models to link this together is probably going to be the best approach. But then the question becomes, well, how do we relate these soil moisture predictions to wildfire danger, wildfire ignition and occurrence, and then subsequent questions to be addressed about fire? So ultimately, the task is to improve the fire risk information so we can help inform fire managers and support decisions after a fire happens. So the study area, as I've mentioned, is the Red River watershed and the Rio Grande watershed. So for those of you not familiar, this is the Red River here that extends from eastern New Mexico into the Mississippi River Valley, right? And so we have a large area, about 88,000 square miles in area. You can see the Huck 4 sub-basins within the Red River watershed here. The mean annual precipitation is driest in the western part, 444 millimeters or 17 inches in eastern New Mexico, and it extends to the wettest zones here, approximately 67 inches or 1,700 millimeters or so of precipitation. In the Rio Grande watershed, we have a much larger watershed to work with. This is about 125,000 square miles, extending from southern Colorado through New Mexico into Texas. And so the mean annual precipitation here is similar. It goes a little bit drier, 7 inches or 187 millimeters or so to 61 inches or more than 1,500 millimeters. The interesting thing is that for those of you that know the Rio Grande Basin, most of this area is not on the dry side, for the majority. It's actually like a 8 to 12 inch precipitation zone across much of the basin. And it's kind of interesting to know that the driest place is actually in southern Colorado. And that's also adjacent to the wettest place, which is on the margin of this watershed, coming in at 61 inches. So in addition to precipitation differences, we have a lot of variability in vegetation communities between these different watersheds. So we have southern high plains transitioning into forested settings here in the Red River watershed. And then of course, in the Rio Grande Basin, we have these expansive basins with mountain ranges that sort of cut through or create these sky islands of higher precipitation, different vegetation communities from bare ground desert scrub all the way up into conifer forests and wetter landscapes. So there's a lot of variability that's present in both these watersheds, which complicates our predictions within the region. The last point I'll mention here is that to kind of call your attention to where the fires have happened. This is data from 1992 to 2013 for fires that are greater than 100 acres in size. And you can see that there are more fires happening in the Red River Basin than in the Rio Grande Basin, which also plays into our ability to understand what's driving those fires. So the first attempt at addressing this objective one is to try to create a soil moisture model or use an existing model to understand soil moisture variability in space and time and with depth. So we decided to use the Java Newhall simulation model, which is shown here in monthly time step, where you've got the blue is essentially a surplus, where you have additional precipitation and low ET. And then the utilization period happens here as the spring warm up begins. And so basically this is for the Morena mesonet site in Oklahoma. You can see that we've essentially recoded this in R so we can replicate that information at the monthly scale. But then, I'll show in a moment, we're trying to take this the next level so we can understand soil moisture at more relevant time steps for fire prediction. So this essentially is a simple water budget model that was designed by soil scientists to understand soil moisture regimes and soil temperature regimes for taxonomy. So we've effectively taken this model and populate this model with the appropriate soil profile characteristics, the depth, available water holding capacity, bulk density, and water content at the critical field capacity and wilting point suctioned, and then make it into a daily soil moisture predictor using precipitation and evapotranspiration to essentially drive the water in and out of this profile with a variety of additions and losses of water through the profile, then we can get this resulting estimate of soil moisture with depth. So just want to get into the details of that just a little bit before I go further. Essentially, you can imagine this matrix is a soil profile where we have the surface here at the top, and we have 10 slices that are at this point 10 centimeters each. So we have these 10 centimeter slices. And then the bottom of the profile that we modeled was 1 meter. And then from along the x-axis here, from the left to right, you have the wilting point, or permanent wilting point. This is the dry side, about 15 bars suction. And then the last column here is actually for saturation, recognizing some soils are going to be saturated. And then the more recognizable field capacity condition at 1/3 bar represents this plant available water. So the blue pixels here represent the available soil moisture for plants to access at different depth increments. So that really takes the predictions of soil moisture to the next level from the previous model. And all this data is populated using the gridded Sergo soil survey product, which is it's pretty much the best soil data set we have available to us. The inputs and so forth are coming from PRISM gridded precipitation data, and then also the ET calculation is based on some MODIS remote sensing estimates of ET as well as calculated values. So the first step was to understand how well this model is performing and sort of train the model on a point measurement. Okay, so this is for a site in southeastern Oklahoma, the Wister Station, for the year 2009. This is so it's a 1-year period. You can see at 2 different depth increments, 0 to 10 centimeters and 20 to 30 centimeters. And so for reference, you can see for these soils, the permanent wilting point value. So what's the volumetric water content at the permanent wilting point, and what's the volumetric water content at field capacity, the blue line here. That's essentially the range where soil provides water to plant roots. And so you can see that the black line here is the measured value at the station for each daily average. And then our colored line here, red for the surface and green for the 20 to 30 centimeter zone, is our modeled values using this R Newhall approach. So I wish all of the validation data looked like this, but I wanted to show you that the potential for the model to capture these changes in soil moisture is there. Although, as you would all recognize, there's always room for improvement, and not all of our validation sites look this good. But this gives us some confidence to say that we can move forward with this model. So we then applied this R Newhall model for the Red River watershed. Essentially, what you're looking at here is a correlation between our modeled values for 4-kilometer pixels to the remotely sensed soil moisture active passive volumetric water content for the 0 to 40 centimeter depth increment. Okay, so the correlation here means that we have better agreement with the green shade than we do with the lighter shades of brown and so forth in the western portion. And really what this is indicating, interestingly, is that there's a pattern of 500 to 600 millimeters of moisture, which starts to happen in the western part of our landscape in the watershed, where there's this break off in the model performance, performing quite well in the wetter zones, and then less so as you move to the drier conditions. So that was the spatial representation. We then took the same data for 1 year, for 2016 is what I'm showing here, to look at how the correlations differ by depth increments. Okay, so the depth increments in the upper meter of the soil, we're comparing this to the soil moisture active passive data, or the SMAP data. And we've got surface condition, 0 to 40 centimeters, 0 to 70, and 0 to 100, where these depth slices that correspond to those zones are aggregated to get the average soil moisture value as a volumetric water content, and then correlated against the similar soil, the SMAP data, right? So essentially, you can see that our red line here, which is the surface, had the weakest correlation and the most dynamic nature throughout the year. And then as you incorporate more and more of the soil profile, green is the next best performing. This is 0 to 40 centimeters modeled. Then we have 0 to 70 in blue, and then the purple line is the upper meter. And so the correlation is going up with the more soil profile estimates that we include. And so this tells us that we should probably be using more of the soil profile, and also gives confidence to say we should be using a root zone soil moisture estimate for relating to these vegetation dynamics and fire. Okay, so I've talked a lot about volumetric water content. You're not all soil physicists, but for those of you that are, and many of you are just thinking about volumetric water content versus, gravimetric water content. Well, and just generally, what is soil moisture? How do we quantify this? You'll know that volumetric water content is influenced by the type of soil that you have. And so those soil properties that drive volumetric water content include things like soil texture, the structure of that soil, especially on the wet side of things, the bulk density. So how much pore space do you have? Organic matter can act like a sponge, so it's affecting volumetric water content. There are other properties as well. So not every soil has the same volumetric water content at field capacity and at the permanent wilting point. So is this really the best measure for understanding how soil moisture relates to vegetation and to fire? Is there some other way that we can incorporate a soil moisture condition essentially then to standardize these soils from one to the other? And so we've had some success, and members of the research team have had success using this fraction of available water. Okay, so if you recall from the previous slide, I talked about the field capacity and the wilting point being sort of the end members of our soil moisture window for plants to take up water. So this is our available soil moisture for plants, right? So this is how big our sponge is with a given soil. And so if we take the measured volumetric water content at a given time, subtract the wilting point value, then we know what the difference is between our measured current condition and the potential for that site. So it translates this volumetric water content value into a more standardized metric from 0 to 1, where 1 would indicate it's the wettest, it's at field capacity, and then 0 would indicate that our moisture is at the wilting point and not available for plants. And so what that does is gives us the opportunity to then apply this fraction available water across soils, across depths, and then make some better interpretations about how that site is responding to a drought or even a wet condition. So our second objective was to start taking the soil moisture data and connecting it to fire danger. And so we used 2 approaches for this. The first approach was to relate soil moisture to the fuel moisture conditions and the fuel load. And then the next approach was to take this soil moisture estimate and try to apply that for fire occurrence. So what's the likelihood of a fire happening with more of a regression-based approach? Okay, so the first part of that is to relate soil moisture to the field condition and also with the fuel moisture, right? Or the fuel load. In this case, this is some recent work by the team that looked at the prediction of wild hay yields across Oklahoma. Okay, so we have essentially 3 years represented, a dry year in 2012, an intermediate year in 2002, and then a wetter year in 2007. And so what you're looking at here is the modeled hay yield in kilograms per hectare and the actual measured hay yield in the same units. And so what we can take away from this is that the model for predicting the hay yield utilized soil moisture data directly to help us understand how soil moisture is related to the production, right? So this is essentially looking at your fuel load. And not surprisingly, I tell you, these are the wetter years. That's why we have more production in 2007 than we do in 2012. But there is a strong relationship here between these data, suggesting that we have better performance with the addition of fraction available water, which is essentially, you could translate this this value 0.65 is kind of sort of like an R squared. So 0.65 versus 0.1 when we did not include soil moisture data in the model. So that gives us more confidence that soil moisture is related to fuel load and also in the fuel moisture condition, sorry. Okay, so we can take the same information with respect to FAW, fraction available water, and relate that to the fuel moisture condition. Okay, so you can see here in the upper panel, we've got mixed fuel moisture condition. And then in the lower panel, we've got the curing rate also related to this FAW condition, right? So the lower FAW is a lower soil moisture condition. A greater value means the soil moisture is higher. And if you take the data from measurements in the field, you can see that there is actually a break point about 0.59 in the fraction available water. So this is really important to understand when the soil moisture is really changing enough to change the fuel moisture and how that's going to translate to the potential for having a fire. The same thing is true about the curing rate of this vegetation. So as the vegetation dries down beyond a certain threshold, then it becomes more susceptible to changing to a more of a cured vegetation, more likely going to be a fine fuel that's going to be susceptible to burning. So if we can start to take some of these different results from recent papers to try to understand how this decline in fraction available water relates to different situations on the ground, we can use this figure here, which is part of a collaborative effort from the team. Essentially, you have wet conditions here where the fraction available water is greatest. And as you dry down the soil, you start to increase wildfire probability here at about 0.6 fraction available water. Also, your fuel moisture begins to decline about 0.59. As you get drier and drier across this curve, you can start to see that your transpiration and growth of vegetation begins to slow when you get closer to 0.4. So you're less than half of the sponge full at this point. The greenness starts to be declining here at lower fraction available water. And then you get the curing that starts to occur. And if you plot that against the number of large wildfires in that same region, you can see that you have more likelihood of large fires in this zone of low fraction available water. And it's important to recognize this is for large fires, because the smaller fires tend to have more variability and uncertainty and prediction ability. So we haven't focused so much on smaller fires because they're less reliable in terms of understanding the soil moisture condition. So large growing season wildfires in Oklahoma primarily are occurring below this 0.2 fall threshold. Okay, so that's true of large fires. I also want to demonstrate that it's not always a clear picture between soil moisture conditions and fall values and our fire occurrence. Okay, so essentially what I'm showing here is data from 1 year in 2016 using fire ignition points from the Monitoring Trends and Burn Severity data set. And you can see this is for the Red River Basin. Again, your red marks indicate fire ignition points, of which there were 121 in 2016. We, in this case, did not discriminate fires that were small from those that are large, which may explain some of this pattern here. But the black dots are random unburned points of the same number. And so these are spatially distributed and then given a start date that correspond to all the start dates of the red ignition points. And so there are some assumptions that are made about how do we best represent these random points temporally when we don't really know where on the landscape it's going to match up the best with the fire ignition dates here with the red marks. To think about soil moisture in this case, what you're looking at here in the plot is for the random unburned points, which are these black dots, and the fire ignition points, which are the red dots or the red marks. This is the averaged fraction available water 14 days prior to the ignition. Okay, so this is for 30 fires during the growing season. And this indicates that it's actually wetter at the fire ignition point for the 2 weeks prior to that ignition than it is for random points. However, I think this demonstrates that one of the challenges of understanding this relationship between soil moisture and fire occurrence is that we don't really know which dates we should apply to these red dots, right? The random points, because it's probably not fair to simply take the dates of the fires and randomly distribute them to this landscape. There's probably a better way to do this, but at this point, I think we can say that it's complicated by the temporal aspect of trying to predict the likelihood of fire. Okay, so if we take the same landscape and look at the non-growing season fires for this 2016-2018 period, and we use a variety of different lag periods out to 365 days. So simply averaging the fraction available water for the day of the fire, the 3 days prior, 1 week, 2 weeks, all the way out to the full year, we can see that we have potential to actually capture some of the burned area, which is measured in the x-axis, and the modeled area of burned area in acres on the y. So there is some potential here to relate the different time windows, the antecedent conditions of soil moisture to fire occurrence, but it's going to take a little bit more time and careful thought to figure out how to best apply this for one watershed, let alone multiple watersheds. So there are some challenges with using our Newhall approach, including the computation time required to model this for the large watersheds that I showed, or even for the contiguous US scale. So I mentioned the SMERGE data set as one of those data that are available that have more continuous coverage, the drawback being that it's a very large footprint, right? Spatial footprint. Nonetheless, we applied this data using a Bayesian modeling approach, using 11 variables, including soil moisture anomaly as one, for 2 different growing seasons, growing season and non-growing season. And I didn't mention before, but the growing season we've worked with is May to October, and the non-growing season is November to April. And we then created 16 different models using these 11 variables, and they were averaged with Bayesian model averaging. That allowed us to get a posterior inclusion probability value for each of those 11 variables to help us interpret what's going on with these watersheds in mind. And so we recognize the importance of a soil moisture anomaly in this spatial and temporal prediction framework. So what we've done is taken the volumetric water content for the ignition date for a given fire. This would be F1, fire number 1, and subtract that from the volumetric water content on that day for all years within the record between 1979 and 2019. Okay, so what that does is allows us to get some essence of what is normal for that particular pixel and helps us to understand the soil moisture anomaly a little bit better without requiring the field capacity and volumetric water content measures. So first I'm going to show results from the Red River Basin. This is very new in terms of obtaining this model. So we're still working to interpret this, but basically you can see the growing season model here in the upper panel and the non-growing season model here in the lower panel. And in this case, you've got the scale is not exactly the same, but red means that you have a higher probability of fire ignition or fire danger, and then the yellow would indicate a lower probability. You can see that there are different patterns for the growing season and non-growing season. And then if we try to understand why those patterns exist, we can look here to our left and see this posterior inclusion probability for each of the covariates that I mentioned. We used 11 of these covariates for this model. So they include some common things like the vapor pressure deficit, the maximum vapor pressure deficit, minimum and maximum temperature for that particular pixel, the precipitation. So this is the mean annual precipitation for that area, the wind speed, which is also taken as an average for that season, the fuel moisture content, also these areas and these bars in red are the potential ignition sources for some of these fires. And so they're rails and different categories of roads. And then finally, I mentioned we have this soil moisture anomaly. I showed the equation, but essentially this is the way to capture how soil moisture might be contributing to the importance of fire in this area by growing season and non-growing season categories. So you can see some variability between seasons. So the bars, the black and white bars here represent the growing season. And so we can see things like vapor pressure deficit, minimum temperature, max temperature, precipitation, adjacency to some of these road categories, but then also the volumetric water content anomaly from SMERGE. That's really important. I should say that the posterior inclusion probability ranges from 0 to 1 and essentially indicates that the likelihood of that variable being in the true model for that area. We can see the non-growing season in the black bars here, similar patterns with soil moisture. So it's really important on this region for having soil moisture represented, but then the variability of other predictors starts to come into play here. So we've got different categories of roads. The fuel moisture content becomes more important here for the non-growing season fires. The wind speed, which is probably related to the fuel moisture content as well. And then some variation in the climate. So there's a lot of complexity here that we still need to tease apart, but I think this is promising to know that the soil moisture anomaly is definitely contributing to these models. If we look at the Rio Grande Basin, again, you can see some seasonal differences between the growing season and non-growing season. And you can see the ignition points here as before, marked by the black squares. And I think there's some important things to note here that within the watershed, we have this north-south gradient where you have higher likelihood of fire for the non-growing season, but that's not shown in the growing season. I think there's a lot of variability within the precipitation patterns and climate and so forth within the growing season, especially spatial variability of precipitation that come into play here. But also I want to point out that there are not as many fire points within this region as we had within the Red River Basin. In this case, we can look at this similar combination of variables. I've just highlighted these again to show them sort of by category. The fuel moisture, again, is more important in the non-growing season than during the growing season, which is an interesting find, I believe. The dynamics of ignition based on roads and rails, again, is variable based on the different kinds of roads. And then in this region, if you recall the Red River Basin, we had a posterior inclusion probability of 1 for both summer or growing season and non-growing season periods, right? But in the Rio Grande Basin, we only see that soil moisture signal being important in the growing season and not so important during the non-growing season. So it may be related to the number of fire points within the region. Also remember, this is a larger basin than we had in the Red River Basin, as shown before. So why do we have some of these differences in soil moisture, and what are some things that are contributing to the fire variability? Well, one thing that's not accounted for in many of the soil moisture models is this spatial connectivity. So this is a Saga wetness index representing a large area in southern Arizona. And basically what you can see is that the patterns of soil moisture would be closely tied to the flow of water across that landscape, right? So this is something that needs to be incorporated at this large scale that's not currently incorporated. And then at a given site, if you were to think about what's complicated my soil moisture model with depth, then you might think the soil is going to be behaving the same in every depth increment, or maybe it's just clear with horizons, but it's not always as clear because you have macro flow, you have distributions of pores and so forth that complicate understanding of the soil moisture and moisture flow within the profile. So these are just a few things that are complicating our ability to understand soil moisture and then how it relates to fire. In summary, I'd like to recognize that the soil moisture predictions with our Newhall they're reflecting the measured values from point measurements across many of the areas in the study region. And they also relate pretty well to SMAP spatially. The soil moisture and wildfire patterns are difficult to interpret, though I think we're making a lot of progress in that regard. Some of the additional issues that might come from our data sets include things like how to best incorporate the fire ignition points themselves, or how do we account for burned area polygons in our modeling. We would need a little bit more longer record of modeled soil moisture with our Newhall to better represent and understand how that relates to fire in the region. But I think that the Bayesian models have potential to help us disentangle some of these relationships. And lastly, I would say that the scale is really important, right? So we have different types of data that cross a range of scales. And this is an ongoing bit of research that will take a few more heads coming together to really make it something we can apply for larger areas. So continuing work that is happening within our group, and then I believe others are starting to pick this up, are how can soil moisture be applied at different landscapes and different vegetation communities or biomes. We need to do some more work on what depth increments are most important. What's the appropriate spatial and temporal resolution for representing soil moisture and wildfire probability? And then, as I alluded to, these antecedent conditions of soil moisture, we recognize they're important, but what's the appropriate window? And then how can we best incorporate this type of information gained into our existing fire danger rating systems. So we did, as a part of this project, we had 2 workshops, and I believe the presentation will be posted later, and they'll be hyperlinked to a list of takeaways that we found from our very first workshop that brought together stakeholders. And many of these questions were brought up at that time, such as the depth increments that are appropriate, what's the appropriate spatial and temporal resolution for not only understanding the relationships, but also doing something with that. We then held a second workshop that highlighted some of the recent discoveries within our group as well as others. And these are really valuable contributions that will help us understand how wildfire predictions can be improved with the application of soil moisture information. So I would like to acknowledge the financial support by the South Central Climate Adaptation Science Center, as well as some other support from the USDA Natural Resources Conservation Service. So thank you for your attention, and hopefully we'll have a little time for some questions and so forth. Thank you very much.
If you have any follow-up questions, please reach out. We are happy to get you guys in connection so that we can have those answered. Also, I will say to sign up for our newsletter, the South Central CASC newsletter, so that you can keep an eye on future presentations that we have. A lot of them are going to be focused towards our funded projects. So again, thank you everybody, and I hope everybody has a great day.
Thank you very much.